128? Sure. You made a lot of progress in the homework. Good job. You're welcome. Okay. So here, this is a solving the logarithmic equation problem. I'm going to do this algebraically. I think it says using any method. I'm going to choose to do this algebraically because at this level, this should be something we're pretty comfortable doing. I recognize right away that I have more than one logarithm. So my first order of business is going to be to compress the two logarithms into one. When compressing, I start the order in which I apply my properties of logs are power, product, quotient. So I recognize there's a power property with the 1/2. And I remember from Algebra 2 that the exponent of 1/2 is the same as a square root. So I'm going to do that. And then I'm going to apply the quotient property because I see the subtraction. That'll take me to there. Now that the logarithm is just or I just have a single log on one side of my equation, I'm going to choose to cancel that logarithm. To cancel logarithm, I need to use an exponent base. The exponent base that I should choose is the one that matches the base of the logarithm. Here, there's nothing written as the base of the logarithm, but I recognize that as log base 10 is correct. Good. That's the common logarithm. So I'm going to do exponent base 10 to both sides. That'll cancel out the log. So I have, already even that way, x over square root x plus 4 equals 10 to the first, or just 10. I'm going to put the first on there to remind us that I didn't multiply by 10, but used an exponent base. So to solve this now, I'm going to start by clearing the fraction. So I'll multiply both sides by the square root of x plus 4. No luck? Okay, no worries. Okay with that? Okay. And again, I'm noticing that I have x's in two different locations, right? What I want to do now is to get the x's out from underneath the square root. So to do that, I'm going to square both sides. So 10 squared is 100. And the square root of x plus 4 squared is just x plus 4. Then I'll recognize that what I have now is like a quadratic equation, right? So I'm going to distribute this through and move it all onto one side. I'm going to do that kind of in one step. Well, that was so fast.
No, it like loaded as I went there. I was confused because it went to like a news website.
Oh. Did Microsoft Edge work? Or did it finally go through on Chrome?
I put it in and it wouldn't load, and then I shut everything down, opened it again, and it all connected.
Oh, well, all right, whatever. We'll take it. So now what I'm going to do is solve this either by factoring or using the quadratic formula. At quick glance, I don't recognize this as something that's factorable. 400 is an awfully big number. There's going to be a lot of possibilities of things that multiply to give me that. I'm not going to bother with it. I'm just going to use the quadratic formula personally. Although it's possible that that factors. And if you saw it right away, good on you. But we're going to just find out together here, I think. All right, so we have 100 squared plus 1600. That's that number. which is not a perfect square. Okay. But certainly that number sure looks like it's divisible by 4. So I can certainly pull a 2 out, right? And I like doing that because I can reduce and get rid of that stupid denominator. So far, so good. And then, I mean, I can probably simplify that radical a little bit more, but I don't really care too much about it. The thing I really want to see is that whether 50 minus the square root of 2900, is that a negative number or not? Because now I'm going to go back and check for my extraneous solutions. If I go back to the beginning, I see that that negative is going to be a problem here, right? Because I'll have a negative inside of the log. So I'm going to know that the negative is no good. So my single solution is just going to be the positive 1. Or you could write that as a decimal, I'm sure would be fine. And I recognize that radical at the end can probably be reduced more. I just didn't feel like doing it right now, to be honest with you. I think that it's what you cared about certainly got done well before this point, and grinding through like how many factors of 2 are in 2900 is not that interesting. There's probably a couple more, but that. Happy?
Yeah.
Yeah, you probably got to the square root part and then made some goof up here, probably.
Yeah, that's
Yep. But again, this, hopefully when you got to this, you recognize this is an Algebra 2 problem, right? You did a whole chapter with radical functions where you solve stuff that looked like that. That's been a year, so like you're excused from not recognizing it immediately, but after you saw it, it's like, oh yeah, we did this. Anyways, who's next? Are there any others? That was a good beefy question. That took a minute. I don't know how long that took. There's a lot of writing. Okie doke. If you change your minds, there'll always tomorrow. Well, or Monday. Nope, Tuesday. We don't have school on Monday. Isn't that amazing? I have to remind myself that every day this week. It's like, there's no school on Monday. I know, right? All right. Yeah, I know. And I think like what is the junior leadership day is Wednesday that week, so you don't even really have classes that day, I don't think. So it's like a pretty wimpy week. All right. So 5.4 continued. In 5.4, we were solving exponential and logarithmic equations. The second part of 5.4 is going to be looking at like real life situations that can be described using either an exponential or logarithmic model, and then answering questions kind of about those real situations. So these will run the gamut of like physics situations or chemistries or earth sciences. I'm just going to kind of screen grab these guys real quick, and then we'll add some examples in after. All right. So we're going to look at 4 different kind of models or situations kind of from the real world. in which like an exponential or logarithmic model will describe that behavior. So the first one we're going to look at is the level of sound intensity, which we measure in a unit called decibels. That's probably a unit you've heard before, whether it's about like how loud the football stadium is or the rock concert or whatever. It's probably a unit that you've heard at some point in a middle school science class or something. The number of decibels is given by the equation beta equals 10 times log I over I naught, where that beta is just the number of decibels. I is the sound intensity that's measured in watts per meter squared. And I naught is a constant. It's always 10 to the negative 12 watts per meter squared. And this represents like the threshold of human hearing, like the quietest sound that a human ear can register. And now obviously that varies individual by individual, but that's like a theoretical, for like the physical makeup of the human ear. In theory, this should be the quietest sound it would register. Now, like if you have spent too much time with headphones in or something and you're kind of deaf, it's like a different story. But, or like rode motorcycles for 30 years or something. Or just like worked at the airport. I don't know. Any number of things to damage your hearing. All right, so let's look at an example. So here it says, given the sound intensity of a busy street is approximately 10 to the negative fifth watts per meter squared, what is the measure of busy city traffic in decibels? So it's asking for decibels, so we know we want to use this equation. It's asking for decibels, so we're going to be solving for beta. We're told the sound intensity is 10 to the negative fifth, so that's our I. And then we remember from the definition that I naught is a constant. It's always going to be 10 to the negative 12th. So filling things in, we have this. Now we should be able to do this in our head with no calculator, to put those calculators away. How do I reduce 10 to the negative fifth divided by 10 to the negative 12th?
Subtract that.
Great, which gives me 10 to the 7th, right? Okay. And then what is log of 10 to the 7th going to be? Again, something you should be able to do with no calculator. 7, right? Because the base of the logarithm is 10. We'll just cancel with the base of the exponential. So we end up with just 7 times 10 or 70 decibels. No calculator necessary, right? Now, would it be okay if you used your calculator here? Yeah, but like give that poor girl a rest, You guys rely on her so much. All right. Let's look at the next example. So here's like an earth science example talking about the Richter scale. Hopefully you recognize that term, right? What do we measure with the Richter scale? Earthquakes. Yeah, that's right. So the Richter scale is designed to register the magnitude of earthquakes. The magnitude of an earthquake, R, can be found using the equation R equals log of alpha divided by T plus B. So the alpha there is just the amplitude of the vertical ground motion. So it's like how much up and down the ground is moving. Everybody's okay with that? And that's at the position the earthquake is measured. So t is the period of the associated wave in seconds. So if a period, what we're talking about, if this is ground at normal, the time it takes to go up, down, and then back to normal, that's the period, just like a sine wave. Everybody's okay with that? And then b is a constant that accounts for the weakening of the wave with increasing distance from the epicenter. So the catch here is that most of the time when you're measuring the intensity of an earthquake, your measurement tool isn't at the epicenter because it's really hard to predict where an earthquake is going to hit and when it's going to hit. So having actually measurement equipment there to measure it at the actual epicenter is impossible, right? So what often happens is we'll take our measurement from wherever our equipment is, and then B is like a correction factor that we tack onto the end. It's like, oh, like 56 miles away, it measures as like a 4.6, but we have to add something to it because it's 56 miles away. So that's something that would be came up with like empirically. Certainly. So that would have been something that like over time we've collected a bunch of data and modeled and like come up with like a conversion factor. But that's something that's just like, at this point, it's like in a table. You just look it up and tack it on, right? Somebody's done that work for us. Does everybody feel okay with the description of kind of what the parameters are saying? Okay. So let's look at an example. This says the infamous San Francisco earthquake had a Richter scale magnitude of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale measurement, or Richter scale magnitude, of 9.5. So at first glance, this feels like maybe there's not enough information provided here because it seems like we're real short on stuff, right? But we need to think about this for a minute. So what is it really asking for? So that would be like the ratio of the amplitude of the more intense or the more severe earthquake divided by the amplitude of the less severe, right? That's what we're really asking for. So we know that we can say we can do that, right? We can write a separate equation for each of these. Now, because what we're given are Richter scale magnitudes, what that means is that the correction factor for whatever that measurement was would have been applied, right? So essentially what that 9.5 and 7.5 is would be a measurement of the earthquake at its epicenter. So what is that going to say about the B's? They're 0, right? if we have a measurement at the epicenter, what correction factor would we need? 0. And from here, since we're given the Richter scale magnitude, like whatever correction factor was needed for whatever measurement they took was already been applied. So we can just kind of like make the B 0 there. Well, that's pretty nice. All right, let's see what we can do now. We'll treat this as an equation. We'll call this equation A and equation B. And let's look at equation B minus A, where we're going to take the more intense earthquake equation and subtract from it the less intense one. So R2 minus R1 is just going to be 2, right? 9.5 minus 7.5. And if we apply the quotient property for logarithms, we can say that, right? Okay. And I'm going to now kind of apply the product property for logarithms and separate that back out like this. And we're going to pause here and think about it because we almost have what we need, right? I see, well, that should be alpha 2 over alpha 1. I goofed that up. Sorry, one moment. Sorry. That's better. And we have almost what we need there, right? Because I see the alpha 2 over alpha 1 inside that logarithm. So let's think for a minute about this T1 over T2 piece. What are the T's representing again? Yeah, the period of that associated ground wave, right? Now, do you think that's going to be a small number or a big number? The amount of time it takes during an earthquake for the ground to do this. That's going to be a small number, right? The ground's shaking really fast during an earthquake. Everybody agree with that? So if I take two really small numbers and divide them together, what am I getting close to? Well, 1, right? If I take two small things and divide them, you're going to get like close to 1. So we know we can say that that's approximately 1. And what's the log of 1? 0. So that piece just kind of drops out of there for us. Approximately. All right? So there is like an approximation going on, but like good enough for us. Because we don't have any information about T1 and T2 to use, so it's convenient that it's like, it kind of doesn't matter. Everybody happy? So my last step is we do the exponent base of 10 to both sides. And we get that the Chilean earthquake is 100 times more severe than the San Francisco earthquake. Ay caramba. Glad I wasn't in Chile in 1960. Well, probably most of Chile would have been fine, but like at the epicenter of that earthquake, I'm glad I wasn't there. Everybody happy with what we did there? little bit tricky because there wasn't a lot of information given and you had to make some assumptions along the way on how to discard some of those variables that we didn't have values for. But like once you've seen that trick for that kind of a problem, it's not too bad. All right, next up, here's a chemistry example. You've done this. Yes, you're going to be a pro. The pH measures the relative acidity of a chemical compound. And it's measured by the concentration of hydronium or hydrogen ions in solution. So the pH is just equal to negative log of the concentration of those hydrogen ions. That's the bracket around the H plus is concentration in chemistry. Some of us are probably really familiar with that. If you're like in the AP or IB Chem course, you probably use that notation a lot. If you did honors chem, do you do it? Do you see that notation in honors chem? I don't remember. Okay, maybe not. If you haven't done chemistry at all, then like you're totally unfamiliar with it. But that's what the bracket around the chemical element or the element looks like. pH solutions are on a 0 to 14 scale. 0 is the most acidic and 14 is the most basic. And then 7, right in the dead center, is considered to be neutral. That is the pH of deionized water. So if you have water that's pure water, like just H2O with no ions floating around in it, should have a pH of 7. So let's look at an example here. A really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two items? Okay, well, if the lemon is 2.2, is my pH equals negative log concentration of H plus. So I'll divide by negative 1 to get the logarithm by itself. And we'll do exponent base 10 to both sides. So the concentration of hydrogen ions is 10 to the negative 2.22. And folks from chemistry, do you remember the unit of measurement that we use to measure concentrations of a mixture or a solution? Molarity would be the most common one. That's what this is measured in. So molarity is just a capital M. That's moles per liter, if you don't remember. Did most of us take chemistry in here at some point, like just honors or regular or some chem, some point? Okay, so we do the same thing for the bleach then. So all the algebra is exactly the same. So that's, again, measured in molarity, moles per liter. And then at part B asks, I think this is a typo, how many times greater is the hydrogen concentration of the lemon than that of the bleach? Because, well, like the acidic thing sure as heck should have more hydrogen ions than the basic thing. So I think that's just a little typo. So we want basically just looking at H plus for the lemon over H plus for the bleach. So that's 10 to the negative 2.2 Divide by 10 to the negative 10.2. Again, no calculator necessary here. What is this going to be? Just 10 to the 8th, right? Or yes, Ava. Of course, yes. Oops, I think I counted one too many there. So just 100 million times more acidic. Whoa, that's a lot. Is everybody so far so good? Again, most of this is, like the algebra side of it is pretty easy. But it's nice to see some stuff where like, when would I need to use this? It's like, here's a bunch of examples of things in the real world that operate either exponential or logarithmically. Our next question is kind of like a, well, I guess this would be like a physics kind of question, like a thermodynamics kind of situation. So Newton's law of cooling refers to the fact that objects that have been heated will cool to the temperature of their surrounding medium. To model this cooling, we use the equation T of T equals T sub m plus T naught minus Tm times e to the negative kt, where T of T is the temperature of the substance after T minutes of cooling. Tm is the temperature of the surrounding medium, so whatever you're cooling the substance in, whether that's a room and it's the air in the room, or like if you're a medieval blacksmith and you're like dunking your sword in a, you know, like a pool of water, or you're putting your, you know, like you're baking in the refrigerator or something, whatever the medium is. T naught is the initial temperature of the heated object. So like what temperature is the sword when it comes out of the blast furnace, or your cake when it comes out of the oven, or your, you know, soup when it comes out of off the stovetop, whatever. And then K is a constant for the given situation. So depending on the material that you're heating, materials are going to cool at different rates, right? Like the inside of a pizza roll like cools really, really slowly. That stuff is like lava hot forever, as opposed to like, you know, like your French fries from McDonald's would seem to get cold in the 3-minute drive from McDonald's to your house. So just depending on what the substance is, those things will cool at different rates. So the K is specific to that substance. Let's look at an example. All right, so we have a hard-boiled egg is heated to 96 degrees Celsius and placed in a pot of water of 16 degrees Celsius water. It should be a pot of water to cool. I don't know why just 16 degrees Celsius pot is not going to help you any. It's going to be water in it. You've made hard-boiled eggs before. After 4 minutes, the temperature of the egg is now 45 degrees Celsius. How long will it take in total to cool the egg to a temperature of 20 degrees Celsius? So reading this question, it should be immediately clear that this is a, you know, like something is cooling. So we're going to be using our Newton's law of cooling problem or equation. So let's start picking out what information is given to us because we're given a whole mess of stuff here, right? So what is the 96? That's the initial temperature. Great. What is the 16? Great, so that's our TM, the surroundings, yep. And what is the 40, well, we have two things, right? We have 4 minutes. That's like our T. And the 45 would be like the T of T, right? That's the temperature after 4 minutes. So that's like, we'd say T of 4 is 45. Everybody's okay with that? And what we're asked then is how long. So we're going to be asking to solve for T when the temperature is 20 degrees. What information has not been given to us at any point? The K. So guess what we're going to be using this is going to end up being 2 steps, right? So the first step is going to be find K, and we're going to be using that T of 4 is equal to 45 to do that. And after we found K, we can use that value of K to solve for T when T of T is equal to 20 degrees. Everybody cool with the plan? Okay. Kind of a confusing question because you're given a lot of information, right? Almost feels like too much information. But that's why. It's because you're missing the K, so you need enough information to get the K. So we'll start with that. So there's my first equation that I'll be solving, right? We'll start by subtracting the 16 over, and I'll combine some like terms. We'll divide by 80. And now what are we going to have to use to cancel that exponent base of e? The natural log. And then the last step would just be to divide by -4. I like writing it as times -1/4 so I don't get confused about whether the -4 is being divided inside the logarithm or outside the logarithm. I kind of use the same rules that I would for what I would do with radicals, so it's super clear to me whether I mean the things inside or under the radical or not under the radical. I like to do the same thing here. You're free to write it however, though, as long as it's clear to you. I like writing it this way. When I go back and I look at my notes, I can't get confused about it. So there's my value for K, about 2.54. Now, the decimal points here kind of matter. This is pretty sensitive. So I'm going to end up just storing this variable into my calculator. So I'm just going to do the STO button and then alpha K, and I'm just going to store that number into the K so I can use it later when I do the other part of this problem. It's just a little easier to do it that way than to have to restart it. And I'm just going to write that as K here rather than write the decimals. So now I'm going to solve the second part of my problem. And again, I'm writing the letter K there, but I'm using that 2.54 approximate value there. So we'll subtract the 16, combine some like terms, divide by 80. Again, I acknowledge that that could be reduced. I don't care, though, because it's all going in my calculator eventually anyway. So, like, who gives a rip, right? Why make it more work for myself than I need to? We'll do the natural log of both sides and then divide by -K. And now it's just going into my calculator. So -1 over, and then I'll call my k that I just stored, divide or times log of 4 divided by 80, and I get about 11.8 minutes. How did I know the unit was going to be minutes? Because the time I used earlier was minutes, right? Yep. What if I wanted this in minutes and seconds? How would I find how much is 0.8 of a minute? Dude, I just multiply it by 60. Don't overthink it. So 48 minutes, or 11 minutes and like 48.5 seconds. Just depends on what the question was asking for. I think this one just said how long, so 11.8 minutes would be definitely appropriate. But if it asked for like minutes and seconds or something, you know, just depends on what the question asked for. But I want to talk about that. Boy, that sounded, somebody was yelling out there, huh? Okay. Do we feel okay on this stuff? Again, fairly straightforward, right? It's just like using an equation, dude. I know, but like we got to talk about it. All right. Last section is on like these financial topics. So one of the main applications is going to be talking about interest. Now there's a couple of different ways of doing that. The first way we're going to talk about is simple interest, which is dumb because nobody actually does this in practice. But simple interest is the only thing that's going to earn interest is your initial deposit. So the equation is going to be FV equals PV times 1 plus RN over 100. FV is just going to be the future value, the value of your investment in the future. PV is going to be your present value, the initial investment that you make. R is your interest rate written as a percentage. And N is the time, really in this case, the number of years that you have something invested. So just as a simple little question here. So if we invest $2,000 at 6%, should say simple there, interest rate, how much money do we have in the account after 3 years? Well, should just be that, right? 2,000 was our initial, 6% is our interest rate, 3 is the time. Push that through the calculator. And I get $2,360. So how much interest did I actually earn on my investment? Yeah. Again, how did we find that? We just took the future value that we calculated and subtracted from the initial investment, the present value. Okay. What if instead of using simple interest that nobody uses, let's be clear, we do compound interest? What compound interest says is that, okay, each time the interest is calculated, the money or the value of the account is going to be used instead of the initial investment. So in year 2, you're going to earn interest on your initial investment and whatever interest you earned in year 1. In year 3, you'll earn interest on your initial investment and whatever interest you've earned in years 1 and years 2. Okay? So the equation for compound interest is FV is equal to PV times 1 plus R over 100K to the KN. So FV still future value, PV still present value, R still interest rate written as a percentage, and still the length of time, probably years. K is new though. K is going to represent the number of compounds per compounding period. Really, in all reality, K is the number of compounds per year. In your question, this will almost always be hidden and not be written as a number in your story problem, but rather as a word. So the common words that we'll use to hide K: annually, that just means K equals 1. Semi-annually, K equals 2. Quarterly, K equals 4. Monthly, K equals 12. Weekly, K equals 52. A lot of people forget that one. Same as the number of cards in a deck, though. That helps. Daily, 365. Again, we're not worrying about any like of the leftovers. We're just 52 is fine. I get that there's like an extra day. 365 is fine. I get that sometimes there's a leap year. Yeah, who cares? Not worth. That kind of detail is not getting in the way of just making things. All it's doing is making stuff more complicated than it needs to be. You know what I mean? All right. So let's take the exact same situation, except use compound interest instead of simple, right? If I read the situation, the only word is different is compounded. What is the K in this situation? 1. Great. How did you get 1? Perfect. Okay. So if I type this in, I get $2,382.03. How come I chose to round it to 2 decimal places? Because it's money, right? We're in American dollars, we round to the 100th because that's a penny and there's no denomination smaller than a penny. Maybe if you're doing like derivative exchanges on the stock market or something, you care about fractions of cents, but in this class, we do not. So the interest here is going to be $382.03. So what was the difference between the simple interest and the compound interest here? About $22. Should I be losing sleep over $22? Yes! Here's why. Suppose instead of just doing this for 3 years, we did it for, I don't know, let's say 100 years. So this is my simple interest. Wow, $14,000. That's great. Compound interest. $678,604.17. Oh, yeah, that's a lot more. A lot more. In fact, it's probably not. It's probably pretty likely that there was a year or multiple years in the compound interest situation where we earned at least $14,000 in interest, let alone the value of the entire simple interest investment. You know what I'm saying? Like, woof, there's a lot. So the takeaway is, over the short term, difference between simple and compound interest, meh. Over the long term, whoa. That's the takeaway. Everybody feel okay with that? All right. So the next obvious question is, okay, so like, does the number of compounds per year, how much difference does that make? Obviously, the difference between like simple interest and compound interest is huge over the long term. But what if we just want to compare like how much doing this annually, semi-annually, quarterly, monthly, daily, weekly, how much difference does that make? Well, let's go ahead and I'm going to do this all in the calculator. I'm not going to write anything down because it's like the same work like too many times in a row for me to it's exhausting just looking at it. So I'm just going to kind of type it in here. And we're just going to update some numbers and observe, right? So this is annually. Okay, let's move it to semi-annually. How much difference do you think this is going to make? $1, $100, $50, $1,000? Let's look. $6.50. Yeah, not much. Okay, well, let's move it to quarterly. How much difference is that going to make? That's got to make even like another $6 then, right? Because we're doubling it. Let's look. Oh, no, it's like $3. Okay, well, let's go to monthly. Here we're tripling the K, right? We're going from 4 to 12. That's got to make a bigger difference, right? No, $3 again. And that's just weekly, though. Here we're going from 12 to 52. That's like over 4 times as much. That's got to really make a big difference. Oh, it's like less than $1. What if we yearly, though? 365. That's so many compounds, right? So many compounds. That's got to make a huge difference. Oh no, like 30 cents. So the moral of the story is, number of compounds per year, not a big deal, right? Like it's better, the more compounds are better, but like, dude, give me a better interest rate than the compounds. It doesn't, in the end, it doesn't make like a huge piece of difference. Everybody's cool with the takeaway there? All right. Let's look at another example using the compound interest. So Mara has $1,000, places it into a savings account with 6% annual interest, compounded monthly. How long will it take before Mara has $4,000? Again, we read this question, you hear compound interest. We know we're going to be using our compound interest formula. What are we solving for in this equation, though? What's the question asking? How long? So we're looking for N. Okay? So what's going to go in as FV? Future value, 4,000. Good. And PV? Good. And R? And K? $12?
Oh, that's me.
Everybody feel good? Okay. So to solve this for n, first step would be to divide by 1,000. And let's go ahead and compute what that, or simplify what that is inside the parenthesis there. Next step would be, excellent, log base 1.005 to both sides, and then divide by 12. So this is now a calculator problem. To get log base of 1.005 into my calculator, I press the math button, scroll down to the bottom and find that log base command. That allows me to type in any base I want to my logarithm. Oops. I swear I pressed the number 4, it just didn't take it. So I get about 23.2 years. Feel okay with that? Okay. Let's do another. Gwen has $600 to place in a savings account. What interest rate would she need, compounded weekly, if she wanted to have exactly $1,500 in 10 years? What are we asking for this time? R. Okay, so FV is 1,500. PV is, R is my variable. K is 52. And N is 10. Okay. So first step here would be to divide by 600. I know I could reduce that more, but I just don't really want to, because it's going to be more complicated than I feel like being at 8:52 in the morning. All right. Now what? I got to get rid of the exponent 520, right? What gets rid of an exponent? Okay, not a square root though. A 520th root. Yep. So then I subtract 1. And multiply by 5,200. And that should be my R, right? All right, calculator time. 5,200 times -1 plus, I'll type in the 520, and I press math and option 5. And then I can do just 15/6. And then close my parenthesis. So 9.17%. How's that feel? Good. All right, I think this seems like a good place to stop here before we get into the next topic. At this point, you guys should now be able to do up through, just let me double check. Uh, 150. Yeah. And that'll be due not this Sunday, but next Sunday, which is the 28th. So this will be, the last assignment will be due the 28th. What does that mean if you have every other assignment completed so far this year? You don't really have to, well, you don't have to turn it in. You should still do it. I'm not telling you not to do it. But if you're like, yo, that saves me a lot of hassle, I'm just going to kind of like go through it quickly and be like, yeah, I got it. I don't have to like do it to do it. But I can do it for me just so it's good enough that I know what I'm doing. You know, save yourself some effort. If you've done all your assignments so far, you can kind of skate by in the last one because that goes up to 184 eventually. So there's a lot of problems potentially there. Anyways, you guys feel good? So next time we'll talk about continuously compounding interest. We'll talk about APY. We'll talk about annuities. Those are the three things that I think we still need to take or to talk about. And that'll be it for the year. Good job, guys.